I am Akash and today I am explaining complex number. So at first we describe why we need a complex number. So let's consider a polynomial x square plus 1 is equal to 0. So if you want to find the root of polynomial, so just find the root of polynomial, that is minus 1. What is this number? This number is not a real number because we know that in a root, square root there must be a positive number. So this number, so we need a new number system, your extended number system with R, that is complex number system, and we denote this number by a symbol I, that is i. So if you want to describe a complex number, what we did, we enlarged R in such a way that every polynomial with coefficient M.Sc has a root in C, where C is a, by C we denote the complex number system, the set of all complex numbers. Now if we want to represent a complex number system in different forms, a set of complex number can be represented as in this form. This is a set of all complex number. We can see as this. That is a Cartesian product of R cross R as a set of all complex number. Now we see a different form of a complex number, that is a algebraic form. How we can represent a complex number in this form. Let's consider Z. Here this sign denotes the belongs to sign. That means Z is a complex number. So how we can represent Z in algebraic form? So algebraic form is Z is equal to A plus IB, where Z is any complex number. Then this is a algebraic form of that complex number, where A denote the real part of Z and B denote the imaginary part of Z. So these are two forms of a complex number. First, if you can see this, that is can be A comma B, that is a R cross R. So we can think that C can be represented in a Cartesian plane because it can represent A comma B, that is a tuple A comma B. So if we want to represent a complex number in a Cartesian plane, that is, this is a Cartesian plane and this is your Z, that is A plus IB, or we can see A comma B. So this is Z, this is my A and this is B. Then this x-axis can be taken as real axis because it represents real part of a complex plane, complex number, and this is your imaginary axis as it represents the imaginary part of a complex number. So this is a plane which represents all the complexes number, and that plane is called Argand plane or complex plane. Okay, so this is a plane in which we can represent a complex number. Now let's understand some basic terms of a complex number. The first one is conjugate of a complex number Z. So let Z equal to, we take algebraic form of Z be a complex number and we want to find the conjugate of Z. Then conjugate of Z is noted by mod z bar and it given as a minus ib, and that is a conjugate of a complex number z. If you want to see in argon plane, so if this is my complex number, then its conjugate is given by this. So this is a representation of the conjugate of z in a argon plane. Now let's move to my second topic, that is, now we understand what is a modulus value of z. Okay, so let z be a complex number and we want to calculate the modulus value. Let first see what is a modulus value. So if is my argon plane and this is my z, a plus ib, this is a and this distance is b. So this length is called the modulus value of z, is denoted by mod z. How can it define? It defined as distance of z from origin, that is, it is defined as oz, the length oz. As we can see, that is represented, z can be represented in this form, a comma b. So we have to find the distance from origin to AB. So by using the distance formula, we easily calculate mod z is equal to a minus 0, b minus 0. That is become a square plus b square. So mod z is equal to a square plus b square. We can write this as a square plus b square. We can also write mod z square as z conjugate, where if we take z equal to a plus ib, this is its conjugate a minus ib. If we normally multiply, we get a square minus b square, that is a square plus b square. Since if I is equal to root under minus 1, then I square is equal to, that is become minus 1. So that is a modulus value of z. Now we move to my next term of complex number, that is the argument. What is argument value of z? As we know, we can represent a complex number, plane number in an argon plane, and that distance is my modulus value. If z is equal to a plus ib, then this distance is a and this distance is b. Then what is this angle? This angle is my argument value. So argument value denoted by a as z, defined as angle between positive real axis and line segment opposite. So this is your positive real axis. So angle between this is called the argument value. But we can see that this value need not be great. What if I revolve from this by 2 pi, then we again get the same line, that is, and this value is theta plus 2 pi. If you again revolve by 2 pi, then we again get the same line, that is theta plus 4 pi. So these all angles are the argument value for this complex number z. So we don't get a unique number. So argument of z can be, set of all argument value of z can be written as theta plus 2k pi, where k is any integer value. and that is a set of all argument value, and it's called general value of argument. What if I want to find the unit theta? Then we talk about the principal argument. So principal argument is same as the argument value. There is only one difference. What is that? It is defined as if z not equal to 0 be a complex number and theta belongs to, remember this interval, this is important, and argument of z is defined as theta plus 2k pi, where k is an integer, then that theta is called principal argument, denoted as ARZ. So what is principal argument? Principal argument is a value of argument such that theta belongs to minus pi to pi. So we have to remember this, that argument, principal argument lie between in this interval. The value of argument such that is lie between this minus pi to pi, then it's called principal argument. Now let's see in my argument plane. First case, what if the z lie in first quadrant? Then how can you find the principal argument? We see in further cases what if the second, third, fourth. But see, let's see what if the complex number lie in first quadrant. Remember this interval, that is our argument of z lie between. Then the argument of this is theta, and if we want to calculate this theta, if I want to calculate this theta, that means this distance is b, this distance is a. Then we use trigonometric function tan theta, and that is equal to b by a. We know that this concept in trigonometry. So theta is equal to tan inverse b by a. Remember this? Here b and a represent the length. We didn't consider minus or negative sign when we are taking the length. So the value of theta we get tan inverse b by a, and that is the value of argument. So in first case, when the z lies in first quadrant, so the theta is lying between 0 to pi by 2. So that lies in the interval. So just simply the argument value of z is value of theta, what we get by this formula. In second case, what if the z lie in second quadrant? Then the form of z is minus a plus ib. Okay. Now we want to calculate this from the positive real axis to line segment OZ, the argument value, and if the argument value lies in minus pi to pi, then it is a principal argument. Since this length is the angle must lie in this interval, so we just need to calculate what is this value. So we calculate this portion. This is a theta. By the similar concept we use here, this distance is a and this distance is b. So theta will again the same value we get. So argument of z is equal to this whole pi minus this angle theta. So in first quadrant we get theta, in second quadrant we get pi minus theta, and we can see that this angle lie in this interval. Now take, what if z lie in third quadrant? So now if we measure this angle is greater than pi, so it not belong to that interval. So in this case, what we do, measure this angle for our principal argument. Remember a simple concept. What is that? If we represent an angle in anti-clockwise direction, that means this angle, then we measure it as positive angle. Okay? But if we measure in clockwise direction, that is this direction, then we take and measure it as negative. Okay? So in this case, we take in a clockwise direction, so we take an angle as a negative. To measure the angle, the argument of z clockwise, we take a negative sign. At first, we measure this angle theta by the same concept. The length is a, this length is b, so we get it equal to tan inverse b by a. So what we do by means a, we subtract the theta. So we get minus pi plus theta, and that is the argument value of z in third quadrant. What if we want to find the argument value of z in fourth quadrant? In this case, we don't calculate this angle because this angle is a grid not lying in this interval. So we calculate this angle in the clockwise direction. So in this case, this is negative. This is a theta. And in fourth case, the argument of value is minus theta. So this is all possible cases. No, there is some case left. What is that? What if z line in this line? That is in this case, what happened? This is my fifth case. What happened in this case? A is greater than 0 and B is equal to 0. Okay. In this case, if you want to measure the angle between the same posterior line segment, that is the same line, so argument of z is 0. What if it lies in here? So in this one, a is negative, b is equal to 0. So here argument of z is equal to this angle, that is pi. We know that the concept that the argument value is lying between minus pi to pi. Equality of pi, so we can take a pi value for the principal argument. In 6, what if the complex number present in that point? In that case, here a is equal to 0 and b is positive. So argument of z can be measured as this angle, and that is pi by 2. If a complex number lies in this axis, that is a equal to 0 and b is less than 0, then argument of z is measured in that sense, that is the clockwise direction, so we take a negative sign, so that is minus pi by 2. That is all about how we can measure a principal argument. Let's do a simple question to calculate an argument of a. So what is the question here? If phi plus r sin theta 4 minus I cos theta, where theta belongs to 0 to 2 pi, is a real number. Remember this, it is a real number. Then find the argument. If a question does not mention the what is the general argument, then we have to calculate the principal argument. So we have the principal argument of sin theta plus I cos theta. We have to calculate the argument for this complex number by using this. So let's analyze it. Solve my expression. What we did, we just rationalize it by conjugate. Multiply it, this becomes 12. This becomes I squared, that is a minus 1. So it becomes sine theta, cos theta. And then we get for a complex part, there's 3 cos theta. And for this, we get 4 sine theta. That is a normal multiplication. Now a minus b, a plus b form, so a square minus b square, I square become 1 as we see previously, so this becomes 16 and this become cos square theta. Now see, as it's mentioned that this is a real number, so imaginary part of this number must be 0. What is imaginary part? This part is imaginary, so imaginary part of that is 0. So take from the information given in question, this expression becomes 0. Why? Because this is a real number, there is a no complex imaginary part in that number. So just solve it. So minus 3 cos theta. So now theta lies in 0 to 2 pi, it's given in question, and this expression shows that theta is in second quadrant. Okay, so now we have two information, the value of sin theta by cos theta, and by using this value we know that the theta lies in second quadrant. So as I described earlier, how we can find the argument value in second quadrant, so let's find it. So the argument value of this sin theta plus I cos theta, here this is A, this is B, is equal to, as in second quadrant, so we just subtract from pi minus tan inverse B by A, that is cos theta by sin theta. To get this value, we get this value from there, just reverse it. So we get 4 by 3. As we know, we take the length, we don't need consider sign. So this is my required argument value for this complex number sin theta plus I cos theta. Now let's calculate a beautiful relation for the integral power of I. If you want to calculate I to power n, where n is an integral, it is a separate part of our video. We want to calculate this I to power n where n is an integer number. So how we can calculate? Just like we have to get this. What is this? Then how can we calculate this? So let's do. In the first start from 0. This is value 1, as you know. I, this is value I square, that means root minus 1 k square, that become minus 1, I cube, that is I square minus I, that is minus I4, that is become I square minus I square, that is minus 1 into minus 1, that is become 1. When we go further, what we see when we calculate I to power 5, that is become I power 4 into I, that is this value is 1, so it becomes I. When we calculate I to power 6, that becomes this becomes I square, I cube. So what we can see that we repeat the values, so we get same value for I 5, same value for I 6, I 7, and we take similarly for I to power 8. So all integral power has only 4 values. It can be I, -1, -I or 1. It doesn't have any other values than this. If we generalize this, then we can see that it can be written as a multiple of 4s. It can be 5 written as 4k plus 1. It can be written as 4k plus 2, 4k plus 3, and it can be written as 4k plus 4. That is again a multiple of 4. So if a number is a multiple of 4, then the power gives the value 1. If we multiple of 4 plus 3, that means n minus 3 is divisible by 4, multiple of 4, then it gives value -8. Similarly, we can generalize all other cases. If we want to summarize this, we can write I to the power n is equal to 1 if n is multiple of 4. It gets a value -I if n minus 1, that is n minus 1 is multiple of 4. If we get the value -1 if n minus 2 is a multiple of 4, and we get the value I if n minus 3 is a multiple of 4. That is the integral power of n. We can see that when we add up all this, we get the value 0. So here we get an observation that when we add 4 consecutive power of any integral power of I, then it comes the value 0. That means if we add in plus 1, in plus 2, in plus 3, then we get the value 0. Then that is a beautiful relation between the consecutive power of i's. By using this, we can solve some problems. Let's solve it. So let's find this value. I 2021 summation I 2022. Now we can directly say this value is 0 because this is a 4 consecutive power of i's. We can also solve it. We want to solve right in the multiple of 4. That is plus 1, this become plus 2, this become plus 3, and this become I mistake here. 5 plus 2, 5 plus 3, and this. Okay, now we can see this in written this form, and by previous we know that this value is I, this value is -1, this value is -I, and this value is 1. So we get the value 0. There's a verification of that result, that when we take a 4 consecutive power, we get the value 0. Now if you want to solve another question, like we have to find this solution n equal to 1, let's take 25. We want to solve this solution. So how can we solve? We can take it easily. We distribute it instead. This is a very hectic problem. So if you want to solve this, we use this relation. Okay, what we did, we partitioned the summation into 4 consecutive powers. Block of 4 consecutive power, and the block is equal given 0. But this is a 2025. We cannot partition into in blocks of 4. So what we did? We write this. Now we can write in this block. This is the total number 2024 that can be divided by 4. So we can write this summation into blocks of 4 consecutive power whose value is 0. The overall value will be 0. So we get the solution as I. So this summation gives the value I. If we want to do a next question, let's take a n from 1 to 13. We want to solve this summation. What we did? So just do first distribute the summation. Now using same concept what we used for previously. We divide block 13, total 13 parts. We cannot divide into 4 blocks. So we write first. Now there is a total 12 elements. So we can write in block. Now this summation and this summation value 0 by the same logic as the previous. So we get I plus I square as the value of the summation, that is I minus 1, and that is a required solution. So today lecture we consider some basic concept of complex number, the mod value, the argument value, how we can find the principal argument, and then we see a beautiful relation how we can find the integral power of I. So thank you for today.